Yes.
Should we submit the assignment today or by the end of this?
End of, it's, well, the end of this week will do. Okay. So if you do it today, that's fine, but if you want to, yeah, that's what it's supposed to be. It'll be marked late, but I won't get to grade them until next weekend. So,
So by the end of
okay, it's time to begin. I have to go by the clock here because this is being recorded. So here we are. This is Module 3. We're going to spend most of tonight talking about life cycles. For those of you who have asked a lot of questions about Assignment 1, I've tried to answer them by email, and in most cases I think I've gotten adequate answers because you haven't responded back. But theoretically it's due tonight, but as a matter of practical matter, I really won't get to grade them until the weekend. So if you're a couple days late, that's not going to matter. The one time when it does matter is at the end of the semester when I have to get grades in, and I don't only have a few days to do grading with final exams and stuff. But right now, it's okay for you to have turned it in now, but keep in mind, Assignment 1, the grading is mainly going to be comments as to whether you got it right, whether you understood it correctly. It's not, the grade that counts is the one you get at the end of the semester in Assignment 1. Okay, tonight we're going to focus on life cycle models. I think I told you this earlier, but just for the benefit of those who weren't paying attention last week. This course starts off with very large-scale concepts and then gradually focuses in on details. And by about 3 weeks from now, we'll be into gory details. It's just so you kind of understand how that works. By the way, I can always tell how far along I am in this semester. The very first day of class, all the seats are filled, and nobody talks during the breaks. As we move along, more people come late, and during the breaks, there's more talking because people get to know each other. So anyway, I can usually tell about where I am in the semester by that. But anyway, okay, we're going to talk about product life cycles tonight. The goal of this module is to look at life cycles in general and product development life cycles in particular, and to talk about that in terms of the project, because software is often developed as part of a larger project. And if you're going to develop the software correctly, especially if you're going to be in charge of the software and managing what goes on, you really have to know what the bigger picture is. So that's why we start with the project level. Now, to begin with, if you're developing a product, there will typically be a number of different kinds of software as part of that product. And we'll see some examples a little bit later this evening. The idea is that there might be a software development life cycle for each of these different kinds of software, and they may be different kinds of life cycles because the nature of the software is different. For example, early in a product development activity, maybe the only software you have to write is software to help somebody test hardware, or maybe to simulate something to help them decide on a design or something like that. Whereas later on in the life cycle of a product, you may have to actually write software that's going to be part of the product. And then later on, you might have to write software that's going to be used to support and maintain the product, or to install it, or something like that, or to debug it. So it's important to realize that you don't just have one way of developing software that you apply to every situation. In fact, part of your job as a manager is to decide for this type of software in this type of situation, what is the most appropriate way to do the development. Now, what do we mean by a life cycle? It's a period of time during which a process occurs. it generally starts with some kind of a concept development or an idea or something, and it usually ends at some point. Now, I'll talk a little more about that in a moment. Another way of looking at it is you can view the life cycle as the context of your process, and by that I mean the big picture view of your process. All of the process details that you go through, all the design and development and testing and whatever else you do, occurs in the context of this life cycle. Another way of looking at it is the life cycle is just the top level view of your development process. You can look at it in all those different ways. The most important thing to keep in mind is that when we talk about a life cycle, a product development life cycle, or a software development life cycle, we're talking about a kind of a big picture view of what goes on, as opposed to when we talk about the details of the process, that's usually talking about the fine details, the specifics of what goes on. Any kind of process has a life cycle. It doesn't have to be a development process. The reason for the word life cycle is that it refers to the process that a living being goes through during its life. It's born, and then it goes through various stages, and then it dies. That's its life cycle. There's a reference there to a paper on that subject. But here's a kind of a very general model of a life cycle. It's a series of phases with milestones that mark the boundaries between phases. The exact nature of the phases, the exact nature of the boundaries depends on the nature of the life cycle. The milestones are the boundaries between phases. And we'll see a little bit later why the term cycle is used. Here's a simple example of a life cycle. Going to school and going to a 4-year college, your life cycle of being an undergraduate student consists of 4 phases. Your first year, the second year, the third year, the fourth year. And that's often called freshman, sophomore, junior, senior. And usually there are some exams that you have to pass. Those are your milestones to allow you to move on to the next phase. Now here's another life cycle. You are conceived, then you go through a gestation period, then you are born, then you become a child, then eventually you hit a point where they call you an adult. Now, if you look at this life cycle, you'll notice a few things. One is that the phases don't have to be the same in length, whereas they did typically for the college student example. The boundaries are sometimes very vague. In other words, normally birth is a pretty clear boundary, but how do you know when puberty occurs? How do you know when someone is no longer a child and they're now an adult? That's not always an exact definition. There's some people sort of gradually do it. Some people I know are never going to become adults. They're going to be children their whole lives. But the point is that the boundaries, the milestones, don't have to be precise. Finally, each individual instance is going to be unique. And that's particularly true with the life of any kind of in this case, it's the life of any kind of an animal. It could be a human, it could be a bear, it could be a mouse, an elephant. They all go through the same life cycle, but the details are quite different. The details of the life cycle of a mouse are substantially different from the details of the life cycle of a person, but they still have the same general model here. Another aspect to consider is that any given phase of a life cycle is in itself a life cycle that has more detail in between. So you can take childhood, for example, and you can break that down into phases. If you have a child and you go to a pediatrician, a child doctor, they will tell you, yes, your child is going to go through these phases, and during this phase they're going to be hard to live with, and this phase they're going to be whatever. And the idea is that this is a hierarchical concept. You can break any phase of any life cycle into more detail. Now here's some alternative life cycles. The one on the top left is one where the phases overlap. You don't necessarily move from one to the next. You may be finishing phase one while you're starting phase two. This is a very common sort of a model for software development, for example. You may have imprecise boundaries. You may have all your phases in parallel. You do them all at once, at the same time. Or you can repeat. You can have life cycles that just repeat. Now this one in the lower right is the only one that actually looks like some kind of a cycle, in the sense of the word cycle implies repeating. The reason the term life cycle is used for other life cycles, like this one here, is that usually part of the life cycle of most species is reproduction, producing offspring, which then repeat the process. So that's why they use the word cycle. But another way to think about it is a life cycle is simply a model to help you understand your process. It gives you the big picture view of your process. And the reason I say this is because too often people assume that they have to follow a particular life cycle model, and that's usually not the case. It is a tool to help you understand what you're doing. Now, there are certain common characteristics of most life cycle models, and if you are doing product development, then the life cycle models have some special characteristics that maybe other kinds of life cycles don't have. Here is a typical product development life cycle. You start by doing research. You come up with a concept that passes some test. Somebody thinks it's a good idea. So then there's a phase where you decide whether you can sell it. It's called a marketability study in some places. Let's say they decide, yes, if you build this, we can sell it. Then you develop a prototype. And the prototype demonstrates that it can be done. And then when you find a prototype that works, then you go through what's called a final development phase, where you basically design the one that you're going to manufacture or produce in quantity. And then you start producing whatever it is in quantity. Think about a product like an iPhone. Somebody did some research and said, yeah, we could do a thing that would have all these capabilities. And somebody said, yes, we could sell that. And so they built a prototype in a laboratory, perhaps. And then they designed the final one, and then they start producing and selling them. This is, again, typical of a product development. If you were working on an airplane or an automobile or a business processing system or a hospital information system or a record system, no matter what you're doing, if you think about it, you can probably map it to this model. You can probably say, okay, we're about here. Now, sometimes you don't always do all these phases. Sometimes you don't. You spend more time in some of these phases than others. But the model is fairly consistent with what happens in most product development. Let's talk about what you see as common characteristics of product development life cycles. One of them is phases. That is distinct periods of time during which different aspects of development are occurring. You're developing a prototype. You're doing a final design. You're doing a marketability study. You're proving a concept, whatever it might be. You also have milestones, which are things that represent accomplishments. You passed a test. You demonstrated something. And you typically have goals for each phase. Why do you do a prototype? Well, the goal is to show that the thing can work, or to show that it can work within a given amount of cost, or something like that. And it's important to know the goals of your phase, because if you don't, you may build something that doesn't satisfy the goal, even though it's an interesting concept. Another thing you typically have with this type of life cycle is what's called an entry criteria, a condition that must exist before you can start a phase. Now, what might that be? Well, you might need approval from some form of management to begin the phase. That would be an entry criterion. You might need to pass a certain test, like the previous phase is finished, or the previous phase has gotten to a certain point. You might need money. Money might have to be approved. You might need people, and people have to be acquired. You might need equipment. The idea of an entry criteria is it's something you have to have before you're allowed to start. An exit criterion is the other end. It's how do you know when you have finished a phase of a life cycle? It's some condition that must exist. You pass your tests. You demonstrate that something will work. Whatever it might be, it's a condition or a test or something that shows that you have met some goal associated with that phase of the life cycle. And finally, you have what are called evaluation criteria. These are principles or rules or standards that you have to meet to evaluate what you're doing. So an evaluation criterion would be something like it has to be a certain speed, or it has to be able to fit into a certain amount of memory, or it has to produce a result that achieves some level of quality, however you measure that. There's an important difference between exit criteria and evaluation criteria. Exit criteria says you are finished. Evaluation criteria says, is it any good? So for example, let's suppose you were going to make an omelet. The entry criteria might be, I have to have a stove, I have to have a frying pan, I have to have some eggs and maybe some other ingredients in order to make my omelet. The exit criteria would be, the omelet is cooked and ready to serve. The evaluation criteria would be, you taste it and decide whether you like it. You might say, well, the omelet is finished, but I don't like it. Then that would mean you met your exit criteria, but your evaluation criteria said it wasn't very good, or it could be very good. It's important to understand the difference between all three of these. There might be an exam question on this, and the reason is that evaluation criteria are very different from exit criteria. Evaluation criteria have to do with the quality of the product. They have to do with meeting standards, meeting accepted criteria of what constitutes a good product. Whereas exit criteria are more likely to be along the lines of you got an approval, you finished doing something, you got the job done. Another example might be, suppose somebody hires you to build a fence. The entry criteria might be you need the wood and you need whatever you're going to make the fence out of, and you need tools to dig the holes and what have you. The exit criteria would be all the fence is up. And then the evaluation criteria might be, does it look like a good fence? Are the different parts of the fence equal and even and painted nicely or whatever? And you can imagine somebody building a fence and you say, oh, well, the fence is finished, but I don't think it looks like a very good fence. That would be a case where the evaluation criteria weren't necessarily met, but the exit criteria were met. Here's an example. The entry criteria answer the question, are we ready to start a phase? The exit criteria says, have we completed a phase? And the evaluation criteria say, do we meet the goals or the expectations or the standards? And very often, the evaluation criteria are used to help decide whether to move on to the next phase. In other words, if you do get done with the phase and you're technically finished, but you think the quality is really poor, you may decide not to go on to the next phase and instead to go back and try it again. The criteria have to be specific. So let's look at some examples. Suppose I say the designers have evaluated the design. Let's say you're evaluating the design phase of a software project, or the quality assurance has okayed the design. These are not very good evaluation criteria because they're vague. How do you know whether the designers have any decent standards for deciding whether it's a good design? A good evaluation criteria might be every requirement can be traced to a design element. Now that would be an example of an evaluation criterion for a design. Basically it says everything you're supposed to do is in there. Another example, the design satisfies a design standard. A design standard might be some set of criteria that good designs are supposed to meet. For example, you may have heard of something called McCabe complexity. This is if you haven't heard it yet, you might hear about it in some other course here. It's a way of measuring the complexity of a design. And a good McCabe number says your design is not overly complicated. It's a simple, straightforward design, and that's considered good design because it's easier to fix and easier to maintain and easier to improve. The coding standards, you should be familiar with coding standards. When you're writing the code, in the writing of a code, your coding standards say you have to follow certain rules when you write the code. You have to put comments in a certain way, or you have to avoid doing certain kinds of things. And that's an example of an evaluation criterion. Do we satisfy the coding standards? Here's an example of poor exit criteria. Management approves the requirements, or the engineers say they're done. Those are very weak exit criteria. Good exit criteria. All requirements have been defined and documented. Requirements have met all standards. Every requirement can be tested. Requirements have been checked for contradictions. Requirements model simulation reports no errors if you're using a requirements model. The idea is good exit criteria are things that are very specific. You can point to them and say it's either true or false. Whereas poor exit criteria, what does management approves of it mean? I mean, it might be a requirement, but it's not a very specific criterion, so it's not a very good criterion. Let's say you're building an airplane and you're in a demonstration phase. Your goal is to produce something that flies and meets certain performance requirements. It's not the final product. You're trying to demonstrate that a particular kind of a design will work. This is something you frequently do if you're building a new airplane. You build a prototype and show that it'll work. So the evaluation criteria might be, does it fly? That's a sort of an obvious one if it's an airplane. And there'll be certain specific performance requirements. Can it do this? Does it do this? Does it? And I'm not an airplane designer, so I can't give you the specific requirements that you'd expect an airplane to satisfy. But if you're building a new airplane, presumably you have some specific capabilities that it's supposed to have. Now, let's suppose you do the evaluation and decide it doesn't fly. Well, then you might decide we're going to have to quit and try something else. Or suppose it flies but doesn't meet the various performance criteria. Then you might decide to quit. This design isn't going to work. Or you might change the performance goals. For example, let's say it doesn't quite meet the goals, but it comes really close. Then you might say, well, let's just knock the goals down slightly because it's good enough. Suppose it flies and comes very close to meeting the goals. Then you might go back and refine the design to tweak it a little bit to make it meet the goals. Or something that happens a lot in real life is you go ahead with the next phase, which is designing the final manufacturable version of the thing, and say we're going to fix all these little problems along the way. Now, this is not you must do this if this happens thing. This is possible outcomes. The idea is that evaluation criteria are usually helpful in making a decision about what to do next. Let's talk about exit criteria. Everything that this phase is supposed to produce, those are called the artifacts, must be complete and have been delivered. Now that seems obvious, but you'd be surprised how often it doesn't happen. For example, you're supposed to produce software requirements and document them in some form. And people say, well, we still haven't documented the requirements, but we know what they are. Well, that means you haven't met this particular criterion. Standards of quality must be met if you have standards of quality. Artifacts must be accessible. Now, what does that mean? Well, here's a scenario that happens quite a lot. There are 3 companies, and they want to win a contract from a government to build an airplane. And the government is going to buy 1,000 of these airplanes. So it's a very lucrative contract. So all three contractors, all 3 companies, build prototypes of what they propose to build. And they all give their prototypes to the customer, the government, and the government picks one. So one is going to be the winner and 2 are going to not win. But suppose the government says, well, I really liked your wing design and I really liked your some other aspect of what this company did, but I really like the engines that this company did. So what I want to do is I want to get you 2 companies to get together, and you have the contract to build the airplane, but you have to buy the engines from here. That's a very common scenario in that kind of a situation. Well, the company over here that built the engines but had hoped to win the contract for the whole airplane might not cooperate very much with this company that beat them out and won the contract. The company might say, well, yes, we have the engine designs, but we're not willing to give them to you unless you give us all kinds of money or make all kinds of concessions that this company may not want to agree. So there may need to be some negotiation. So that's an example where the work is complete, but it's not accessible. The engines have been designed, they're good, they meet all the criteria, but this company doesn't have access to them until this company over here is willing to give them the information. So that's what I mean by accessible. There's various other examples where you build something, but you aren't allowed to have it for reasons such as contractual differences, political battles that go on, etc. There might be legal obstacles. For example, there are situations in the arts where somebody, let's suppose that I got the wrong button here. There we go. Let's suppose you're putting on a play, and you've decided that you're going to sing 10 songs during this. It's a musical play. And you're all ready to put the show on, and everybody's practiced, and everybody knows what to do, except that somebody who owns the copyright to one of the songs won't give you the permission to use it because they own the rights to the song and they don't agree with the contract that you've given them or whatever. So that's another example where there's a legal obstacle the song is there, everybody knows how to sing it, but you're not allowed to sing it without getting their permission. That's an example of something that might happen. Okay, or another example is a company that supplies the stuff goes bankrupt. And so you can't access it because it's all tied up in some kind of legal proceeding to resolve the bankruptcy. Lots of issues like that. Now, one of the things that you find in some of the newer methods of software development is that they make schedules where instead of defining the schedules in terms of time, they define them in terms of results. When this happens, we've met milestone 1. When that happens, we've met milestone 2. And you don't tie it to a specific schedule. You just say, when this is done, then we'll go on to the next phase. And the idea of this is that you don't create artificial pressure to meet a deadline when you just cannot get done by that deadline. Anyway, I just thought I'd pass that along. The purpose of exit criteria is to make sure you actually did what you claimed to do, and that you didn't take unnecessary shortcuts just to meet a deadline. And so the idea is you define your exit criteria to make sure that it's really finished. Entry criteria are things like funding and approval that you can't begin until you have, because you are either not allowed to start or you don't have the resources you need to start. One of the ones that I've run into is this last bullet here, ability to understand and use the results of a previous phase. Now, what do I mean by that? Well, let's suppose the previous phase was a prototype, and now you're doing a final product development based on the prototype. And somebody else did the prototype, and it works. But they didn't bother to document the design. So they want you to do the next phase, but you don't know how the design works. They say, well, Joe knows how it works, but Joe just quit, and nobody knows how to make it work. So you have no access to the information, even though in some theoretical sense it exists. Or one that I ran into once is the prototype was developed by a company in another country, and we couldn't understand their documentation because it was all written in a language we didn't understand. So, or the notation they used was not standard and nobody understood it, or they used a programming language that we're not familiar with. We don't know how, we don't understand the code, that sort of thing. Those are all examples. Okay, now remember that each phase can have sort of a miniature life cycle as a sub-life cycle, if you will. And what you typically do as a manager is you try to keep breaking things down until you get to the point where you have relatively small pieces. This is what you did in Assignment 1, those of you who've actually done Assignment 1 by now. You broke the job of taking this class into smaller and smaller pieces. All right, now let's talk about projects and life cycles. Here's some terminology that I will use, and it's not always used exactly the same way, but here's how I'm going to use it. The term program is usually used to mean either a really big project or a project that consists of a lot of smaller projects. So here's a typical example. A program may have 3 projects. Let's say the program is to build a new airplane. This is a project to build engines, this is a project to build the fuselage, and this is the project to build the wings, or something like that. The idea is that the way you typically break a big project down into pieces is something like this. And then somewhere down in that hierarchy, you'll see software projects. Build the software for the pilot to use in the cockpit. Build the software to control the landing gear. Build the software to control the heating and cooling inside the aircraft. Whatever. Projects come in various sizes. They can be something that lasts a week. They can be something that lasts 10, 20 years. If you've ever been on a project to develop a ship for the Navy, for any country's Navy, you know that those things take 10, 20 years to do. Those are big projects. Now, generally speaking, when people talk about a program and a project, the program is a bigger thing than a project. But these are not precisely defined terms. So some people will use the term program where someone else will use the term project. And so I just warn you that these are not precisely defined terms. But generally speaking, a project is a little more focused, and a program encompasses a lot of projects. Here's an airplane. It has many parts to it, and they may have a project associated with each part. And each part may have a different company or a different group of people developing it. A program is the thing that coordinates all those parts so they all work together. And you can have very many layers of hierarchy in a big program. There's also what I call a technical hierarchy. A program encompasses a lot more than product development, and it involves marketing and sales and installation and support and all sorts of other factors. Whereas typically there's a technical hierarchy. At the top level, maybe you're building the airplane, and then you're building the engines, and then you're building something that goes into the engine, and then so forth and so on. The technical part of a project has to do with the things that you typically use engineering skill to produce. The mechanical parts, the electrical parts, the software parts. The non-technical aspects of a project are things like the financial issues, cash flow, how you pay people, acquiring facilities, all that sort of stuff. And at a program level, you have to coordinate all that stuff. For example, you may need, let's say you're going to use Java to develop some of the software. Somebody has to order the Java compilers or whatever you might need. And maybe you're going to need a database to store things. Well, somebody has to build the database, and somebody has to decide how all that fits together. An integrated master plan is the plan for the whole project or the whole program. And the reason they call it integrated is it means all the different parts tie together in your integrated plan. The integrated master schedule is the schedule at the top level. It's the way it looks to the overall project or program manager. And all the software schedule and the electrical schedule and the networking schedule and the mechanical, if there's a mechanical part, they're all subparts of this overall integrated master schedule. I'm going to say more about them later, but it's important to keep in mind that these are program level things or project level things that software fits into somehow. Another way to look at it is you have a system, and then you have the technical components of the system, and then you have the software that belongs to parts of those technical components. So the real point here is that software is always part of something bigger, particularly in a major product or major project that's going on. If you're building an assembly line for some purpose, doesn't matter whether you're making cookies or making automobiles. If you're designing an assembly line to produce these things, there's a lot of software involved. But there's also a lot of mechanical stuff, and there's an awful lot of other things that go along. So, your system might be an airplane. The engineered parts of the system might be all the physical, mechanical parts of the airplane, but that's leaving off all the other things like the design and making sure the seats have enough space, all that. And then you have software which fits into all those things in various places. So, you have a product development life cycle, which is the life cycle as it appears to the program or project manager. And then you have what I call the system engineering or system analysis life cycle, which is the way it looks to the people who are handling the technical part of the project. And then you have the software life cycle, which is the way it looks to the software developers. In this module, we're going to talk about the product development life cycle. In the next module, we're going to talk about the system engineering life cycle. And in the last module tonight, we're going to talk about the software life cycle. So, I talked about this before. The product development life cycle typically has a bunch of phases. It doesn't have to be as rigid as I've demonstrated here, but you typically have many software life cycles. For example, software to simulate the system, software to test the hardware, application software for the product, maintenance software to support the product. Those are all different kinds of software that you may have to write to support this system or this product, and they may all have different life cycles, and we'll see more about that later tonight. Here are some concerns associated with systems that have software in them. And they are typically things that are not often discussed in your basic computer science courses, like warranties. How many computer science students know how they should deal with warranties on their software? If the boss says, we want to give a 10-year warranty, how much is it going to cost us? Well, most people have no idea how they would figure that out. How do we determine how much maintenance is needed? What documentation do we need to have and why? There's all sorts of things like that that are of concern to the person running the project, but are not necessarily of concern to the software developer. But if you're the software manager, you are probably going to need to pay attention to these things. Appendix A has some more details about a particular kind of life cycle when you are buying a government project or bidding on a major government project. It's probably overkill for what most of you will run into in your careers, but I put it out there just for reference. It's not on the exam. Appendix B is some additional reference material specific to U.S. government contracts. Again, not on the exam, just for reference. Now, what is your responsibility if you're the software manager relative to the product development lifecycle? Well, first of all, you need to know what it is. What is the big picture? And where are you in that big picture? What phase are you in? What are your current goals? What has been accomplished? What was supposed to be done in the previous phase, and what was actually done in the previous phase? Sometimes those are not the same. And often the difference matters to software. For example, the previous phase was a prototype phase. They were supposed to produce some requirements for software, but they ran out of time and didn't bother to do that. So now it's the next phase, and you have to manage the software, and you don't have any requirements. Well, you better be aware of that, because it's going to affect how you approach your phase. Know what's supposed to be done in the next phase, so you know what the overall goal is and where you fit in relative to that goal. For example, let's say the overall goal is for the airplane to fly, and you're developing software. Well, you probably better put top priority on anything that relates to whether the airplane can fly, and not be quite so concerned about nice features that are required but are not essential to the overall goal of having the thing fly. Now here's an example I've shown before of a project life cycle. And as a software manager, let's say you say, here's where we are. They just finished the prototype, and they approved it, and they gave the okay to go into final development. Well, that would be important for you to know. What was supposed to be done here and what was actually done here are questions you should be asking, particularly if they influence or affect software. What is supposed to be done there? Because you're going to be held responsible for getting the thing on the right accomplished, at least the software part of it. And if the part on the left, if you were assuming the part about what was supposed to happen, and you make plans to get this done, and then you get started and find out that what they actually did wasn't what they were supposed to do, you've got a problem. And this is a very common problem for a software manager. Typical problem, the prototype software was developed, intended to be thrown away. Prototype software, right? Throwaway software. So it wasn't written with the intention of being long-term reliable or maintainable, well documented, tested. It was just something to make the prototype work. Very common scenario. Now it's time to do the production, to design the production quality version of the software. And your manager says, well, instead of throwing away all that prototype software and starting over, we want you to take the prototype software and make it work. Well, you look at it and you say, it's not well documented, it's sloppy, it's really awful code. You've got a problem. Well, you need to be aware of that rather than being surprised by it. How do you address this kind of a problem? Well, one thing is educating project managers and program managers on the difference between a prototype and a production. Because if they don't understand software, they may not understand the difference. They may say, well, it works. Why can't you use it? And you may have to come up with a creative way of explaining to them that it's prototype software, it's junky software, it's not written well, it's not documented well, it's all the things that you might say it doesn't meet our standards, it's poor quality, it's going to fail, it's going to have lots of bugs, it's going to be expensive to support. You need to be able to make your case to them. You might even point out liability issues. By the way, there are lawyers who study these things and look for situations where somebody takes prototype software and tries to put it into a final product, and then they sue them because of incompetence, because they put sloppy software in the product. I've had lawyers taking computer science courses so they know what constitutes good software and what constitutes bad software, so they know how to sue you if you produce bad software. So that's why I mentioned the liability. And another thing you can do is you can gradually replace the prototype part with good quality stuff if you can't just throw it away. Sometimes you can't throw it away for political reasons. Here's an example. A government laboratory develops some software and they give you a contract to do the next phase of the project provided you use their software. Except their software is really poorly written. It's really sloppy. It's just something they did in a laboratory to prove something. So you can't just say we refuse to use it because it's junky software because they're your customer. So instead you have to say, okay, we're going to incorporate it, and then little by little you throw it away, but you do it in pieces so they don't notice that you're replacing the whole thing. Okay, another problem. You didn't produce the software specifications in the previous phase that you were supposed to because they ran out of time. Generally speaking, producing the software specifications is the last step of a prototype phase. And if they run out of time, guess what doesn't happen? The last step doesn't happen. Well, you may have to institute a specification development activity that wouldn't normally be part of your activity. System requirements are not firm, even though they're supposed to be. A very common scenario is there's still a lot of uncertainty in this requirements at the higher level. But you're supposed to base your requirements on these higher level requirements. And if they're not firm, what are you supposed to do? Well, this is where you use an incremental development process where you build what you think is pretty firm, and then hopefully by the time you get that done, some of the system requirements will have firmed up, and then you can start working from there. The project is staffed by people who are very good at developing prototypes but aren't very good at developing production quality products. There's an awful lot of people who are really smart, but they don't have what it takes to produce high quality results. They produce really clever software, but they're not very good about making it robust, not very good about dealing with what happens if there's a power failure in the middle of what you're doing. Well, yeah, if you have a power failure, let's say you have a temporary power failure and you're flying an airplane, you don't want the computer to go blank and then reboot and take 20 minutes to reboot. You know, that's not going to work. But so building it to be robust is harder to do. And it's the kind of thing that some people are good at and some people are not. Another thing you can do is educate people on the difference between a prototype and a production effort, because a lot of the time the managers don't understand the difference, and then they make decisions based on the way the prototype works. Let's say when you developed the prototype, you were able to proceed at a certain speed because you were sloppy. You didn't bother to thoroughly test it. You didn't need to. As long as it sort of worked, you were okay. On the production quality version of the system, you may not be able to get away with that. You may have to do a more thorough job of testing. Another thing you can do is if you don't have people who know how to do a final high quality product, You acquire a few people who know how to produce a high quality product and put them in key positions in your organization so they can kind of teach the other ones how to do it. I learned an awful lot from people who had been through that process and knew how to produce a high quality product. For example, something I learned that I never learned in a university. You have a supplier building software for you. You have to make sure that when they deliver something to you, what they deliver to you is exactly the same as what they demonstrated when they proved that it worked. Usually there's some kind of a final test to prove that it's good. And then they ship you the software. And then you get the software in your hands and you run it in your environment, it doesn't work. You find out, oh, they made a few tweaks along the way. They changed it between the time they did the final test and the time you got it because they wanted to make some improvements, and then it doesn't work right. That's a common problem, and if you've never been in that situation, you don't necessarily appreciate how serious that can be. So you have to have a mechanism to make sure that the thing that they demonstrated is exactly what they delivered to you. It's a simple example of a lesson you learn doing real projects. Okay, most real projects don't have the kinds of life cycles that are in the textbooks. They are typically heavily tailored, modified versions of those life cycles. But the ones in the textbooks are a very good idea to study in order to sort of understand the basic idea of how things work. Okay, to summarize this module, a life cycle model helps us understand a process by breaking it up into parts. The product development life cycle typically involves phases and may have both technical and non-technical elements to it. You have to coordinate all that, and that's what the program manager or project manager does. And you may have different kinds of software life cycles for different kinds of software. That's the end of the module, so we're going to take a break. We're going to take an 8-minute break and then resume with the next module. Okay, let's now move to Module 4, Systems Engineering Life Cycles. The goal of this module is to look at the process from the perspective of the system engineer. This is the system analyst, the person who is designing the complete product, not just the software part. The chief technical person on the product. And then look at how software fits into that. This is the system engineering life cycle is the life cycle as seen from the perspective of whoever's in charge of the total technical structure of the product. It incorporates all the different disciplines that might be involved. For example, if you consider a product like a smartphone, somebody had to design the mechanical case, somebody had to design the radio, someone had to design all the electrical circuits, someone had to design the software, all the different disciplines that are involved in designing that phone. And then the system engineer is the person who sits above all those people and makes sure all the different parts come together into a really fully functioning product. Typically, this life cycle starts with a concept of what you want and ends with what's called system integration, putting it all together. Software engineering has to depend on good system engineering in a major project. This is a picture of a typical system. It has what are called subsystems, different parts of the system. Sometimes these are called segments. And they get down into smaller systems, and this hierarchy can go several levels. But eventually you get down to what's called a product or an item or a configuration item. One of the issues you run into here is that the terminology varies from one project to another, from one industry to another. So you'll see all these different words used, and they don't always mean the same thing to different people. So you have to know what terms are used in whatever kind of business you're in. But eventually you get down to these things that are called configuration items, and those tend to be the things that software managers are responsible for building. Not necessarily all of them, but the ones that are composed of software. Here's an example. You're building a personal computer. It has a keyboard, a system unit, a display, and a printer. And the system unit has a power supply, a processor and memory component, and some system software. Now you, the software manager, might be responsible for just this system software portion of the product. Somebody else is building the processor and memory. That's typically an electrical engineer. Somebody else is doing the power supply, and meanwhile somebody else is doing the display. That might be a mechanical engineer or a combination of mechanical and electrical engineers. Maybe there's some firmware or even software in there, and so forth for all the different parts of the PC. Now this is a very greatly simplified picture here, but the idea is you might be responsible for this software, which is part of this subsystem, which is part of this system. Now this is what the life cycle looks like from the point of view of the system engineer or system analyst. The first step is to understand what the customer wants, and then to design a system that accomplishes that. And part of that design is what's called allocation. That is, you decide what are the parts and which part does which thing. Then step 3 is to build the parts, and this is where the software manager typically comes in, because some of those parts are software parts. And then finally there's the integration and test, which means put it all together and make sure it all works. Now if you have a very complex product, this will occur in layers. So you at a top level, let's say your product is an automobile, you might say, okay, the parts include the engine and the transmission and the chassis and the this and the that, and there might be a dozen parts to an automobile. For each of those parts, you go down to this next level and define, you do the same process for the engine, you do the same process for the transmission. And then you break those parts into smaller parts. And you go through this process again and again, except that each level you do it multiple times, and then to the next level you do it even more multiple times. But eventually you get down to these, if you will, these components that you no longer go through a system engineering process on. Instead, you assign them to someone. Like, okay, we require a database that has this functionality. And software guy, you're in charge of that database. And then it's up to you to build it. But all the higher levels were done by systems engineers or system analysts. So let's look at these 4 steps. And again, they occur at each level in the hierarchy. If it's a complex product, there's many levels in the hierarchy. By the way, you can also repeat these steps over and over and over again. I'm trying to make it simple here. The first step is called system requirements analysis. It's where you analyze the requirements. What does the customer want? And the output is what's called verifiable specifications. Now, what do I mean by that? That means here is what I want, and here's how I'm going to verify that you've given it to me. Now, it's not always this simple. Sometimes you have to go through this process multiple times because at the first time around the specifications are very vague in certain areas. But the idea is the goal of the analysis phase is to take what the customer wants and translate that into very specific things that you want done. Those are called the system requirements. They are requirements of the automobile or the aircraft or the payroll system or whatever it happens to be. The customer typically has no idea of how to technically produce the thing. They just know, I want a car that is fast or something like that. And the system engineer translates that into very specific requirements. It has to accelerate in such a way, it has to brake in such a fashion, and so forth. Now, an engineering requirement at this level should be documented, and it should be a need that must be met in order for the product to satisfy its purpose. Well-documented requirements say what are the characteristics that the thing has to have, what capabilities, what qualities, and very important, how will I verify that we have satisfied these things? And the reason that's important is because that's how you tell whether you're specific enough. If you don't know how you're going to verify it, then you really haven't defined it well enough. If you say, I want an attractive-looking car, well, how do you test that? You have to define how you're going to test it. You're going to show it to 100 people and 95 of them have to like it or something like that. You have to define some way of agreeing on whether it meets the criterion. And one of the steps in doing that is to confirm this with the customer, if you can. Sometimes that's hard to do, but to the extent that you can, you want to go back and make sure you understood, did you really mean for me to be able to do this? I remember a very specific example that sort of illustrates this. My father one time was trying to order steaks from a butcher. And he was really unhappy that the steaks he had been getting in the past were very thin. He wanted a thick steak. So we went to the butcher and he said, I want my steaks to be 1 inch thick. Well, that's what the butcher gave him, steaks that were 1 inch thick. And he said, oh, I didn't really want them that thick, but it turned out that's what he gave him because the customer tends to not always be very good at being precise and accurate in what they say they want. So a system engineer has to kind of work their way through that and figure out what they really want. Okay. Software can support this activity in several ways. For example, you may need to use a simulator to simulate something so you can better specify what you want. Well, software may have to write the simulator. Yes?
If we consider lab projects, lab software, since we have to develop the lab software, then how we can interact with the end user?
Well, that's a good question. How can the software guy in the lab developing this software interact with the end user? Sometimes you can't. Sometimes you have to interact with the system engineer or the system analyst and hope that they get the end user's intent correct. That's always a difficult issue. You'd often see sometimes the system engineer can explain it better than the end user can. And so this is all a matter of what is the nature of the product, what is the nature, how good is the system engineer, et cetera. There's not a simple answer to your question. Okay. You don't yet know what kind of software is going to be in the final system, but you still may be needed to write software to help them define that. For example, you may have to analyze data to figure something out. One of my very earliest programs that I ever wrote was they had specifications for trucks. I was working for Ford Motor Company, and I had to analyze the specification and figure out how much steel needed to be in the truck in order to hold enough weight to meet the weight requirements. I wasn't designing software that goes in the truck. I was designing software that would figure out how much steel needed to go in the truck. Okay. Often there will be a need to analyze different algorithms or to develop algorithms to do certain things. So there's plenty of things for software to do during this phase, but it may not have anything to do with the final end product's application software. Step 2 of the system engineering function is a design step. Now that they know what needs to be done, now they design a solution that will accomplish that. This is defining the architecture of the solution. It's a synthesis activity. And one of the things you run into is that some system engineers are very good at analysis, some are very good at synthesis. Most of them are not so good at both. So sometimes you have to work that through. But basically they're going to say these are the parts of the product, and here are the interfaces between the parts, and here's the requirements for each part. So they take whatever those specifications were that you did in step 1 and translate that into what's called a design specification and an interface specification. The design specification is very high level, but it says, okay, we're going to have this here, and we're going to have this here, and we're going to have a component here that does this function and a component that does that function, and we're going to communicate over this kind of a bus or whatever it might turn out to be. A major task of the system engineering function at this point is deciding what the parts are and how they connect to each other. And they typically define this in terms of various kinds of design specifications, interface specifications, diagrams, and so forth and so on. And if you were taking a course in systems engineering, you would be learning how to do some of these things. Here's an example of a very simple system. A sensor is supposed to detect signals. Let's say it's detecting temperature. And so you have an analog device. This would be something that responds to temperature. Think of a thermometer. and you have what's called an analog to digital converter. This is something that takes the analog signal from your analog device and converts it to a digital signal. This is an electrical device. And then software would look at that electrical signal and do something with it, like display a number on a screen or something like that. That's how a sensor would work. And there's all kinds of sensors. So, for example, you can sense temperature. You can sense smoke. You can sense humidity. You can sense various kinds of things. A radar system can sense whether there's some device out there that's moving. There's all kinds of sensors. I just got a new car about a year ago, and it has a parking sensor. It can tell whether you're within so many feet of some object so you don't run into it. I don't know how it works, but it's something very similar to this. But the analog device detects that I'm close to something, and it converts it to a digital signal, which goes into some software, which sends a beep and tells me you're too close. Allocating requirements is a very important part of this activity. This is deciding, let's take all the requirements and figure out which component implements which requirement. And sometimes it's not that simple, as I'm going to show you. Sometimes it's straightforward. The requirements can be directly translated to components, as is indicated here. But sometimes the requirements have to be broken up into sub-requirements or analyzed in different ways, as I'll show you in a moment. Then you have to document how you have allocated these requirements somehow. I'm talking about a large system where you can't just remember it all in your head. This is sometimes called a system design document, or maybe there's some other kind of a document. There's all kinds of names for documents that tell you which requirement has to be met by which component of the system. Sometimes there are what they call derived requirements, and I'll show you an example of that. A derived requirement is not an original requirement, but it's a requirement the system designer has to put in there in order to accomplish the real requirement. And I'll show you an example in a little bit. So what they're doing is they're taking the design, and then the next thing you do is say, let's translate that into requirements for each component. These are the requirements that the software person is going to use if the component is a software component. These are not requirements that came to you from the end user. These are requirements that came to you through the system engineering process. You repeat this process down the hierarchy into more and more detail until you get to the point where the thing that you are specifying, the component, is like a piece of software. How many levels of detail? It depends on the size of the product. If the product is a simple sensor, it's probably 1 or 2 levels. If the product is a battleship, it's probably 50 levels. So it just depends on the complexity of the product. The configuration item is the thing at the bottom. It's from the system engineer's point of view, it's the individual component that the system engineer doesn't pay a whole lot of attention to the next level of detail. A hardware device might be a configuration item. For example, a circuit board that does a particular function, or a chassis that performs a particular function. A software configuration item is sometimes called a software item. Sometimes it's called a computer software item. There's all sorts of names for a configuration item consisting entirely of software. But those are the things that the software manager is responsible for. If you're using object-oriented design, you can run into trouble, because when you do an object-oriented design, the objects and classes that you come up with may not directly translate into components the way a system engineer would like to see it. So sometimes you have to figure out the relationship there. Now, one of the things you need to find out is where is the software in the system and what role does it play? And that person who worries about that is sometimes called a software system engineer. It's a person who's kind of on the border between the software engineers and the system engineers. It's a person who's trying to understand the design of the system and understand the design of the software and figure out how to make it all fit together. For example, they decide we're going to put microcode here and we're going to have software there and we're going to load the software in this fashion, thinking it kind of at a high level of how that's all going to work. Now, what to put in software and where to put it is something that the software person is usually very good at figuring out. The system engineer may not be. So one of the jobs of a software technical leader is to make sure that those decisions are made appropriately. I've been in situations where a system engineer who didn't understand software would define this piece of hardware that should do a function. And the software engineer looks at it and says, I could do that in 100 lines of code. You don't need that complex circuit board to do that. All you have to do is give me a microprocessor and I can make that a minor little subroutine. And the system engineer in that example didn't understand how easy it would be to do that function in software. That's because the system engineer has to understand something about mechanical engineering, something about electrical engineering, something about networks, something about software, and sometimes they aren't familiar with all that can be done. So the software team must make sure that they're aware of what's being discussed, that they're in on the conversation, and that they're making sure that people understand, hey, you could do that in software. Okay. A very common mistake of system engineers is either to not understand how much of the system could be done in software or to underestimate how much software you need, because they may think it's a really simple thing to do in software when in fact it's really complicated. A large system will have many software configuration items. And you may have some configuration items that, for design reasons at the system level, consist of both hardware and software. Figuring out what the configuration items are is a very important job for the software manager and the chief technical person on the software team. We're going to talk more about that. Possible exam questions. Give 2 reasons why software expertise is vital to good system design, even if the system is mostly hardware. One possible reason is to help identify where software can do the job. And a second reason is to make sure you have the right software configuration items. And we're going to talk in a little bit about criteria for a good software configuration item. In fact, we're going to do it right here. Ideally, a software configuration item or software item would have these characteristics. It can be developed independently of the other ones. So you can give it to a team and say, you do this one. It can be tested independently of the other ones, at least up to a certain point. It could potentially be sold separately or updated and maintained separately and supported with its own set of documentation. So think about Microsoft Office. And to simplify it, let's assume that Microsoft Office consists of Word, PowerPoint, and Excel. If you were in charge of Microsoft Office, the logical 3 configuration items would be Word, PowerPoint, and Excel. Why? Because they can be developed independently. They're pretty much independent of each other. They could be sold separately. They could be maintained and updated separately. But by contrast, you wouldn't take a product like Word and say, we're going to break it down into the user interface part and the database part. You typically wouldn't do it that way. I mean, it might be organized that way, but you wouldn't tell the customer there are two parts and you have to buy both parts. You know, you'd tell them you need to buy Word, but it wouldn't make sense to tell the customer you can buy Word separately from Excel, because there are two different functions. They do two different things. They're two independent things. So the software manager has to decide what those configuration items should be, and these are some of the most important criteria when deciding that. Here's some other considerations. A software item might run on a different processor in a multi-processor environment. You're going to run into that with the Mr. Television project. Or it might be done in a separate language. In other words, you might say this configuration item is written in Java and runs on the processor that talks to the network, and that configuration item over there is written in C++ and it runs on the main processor and does something different. Now, occasionally you run into this very pragmatic problem. Sometimes there's a particular part of the system that the customer or your higher level management is really interested in. A good example is a database. Sometimes they are really concerned about the database. Why would they be concerned about the database? Maybe they had a lot of trouble with the database on the previous project, and so they're really worried. Or maybe you're doing some innovative kind of database design and they're really concerned that it might not work. In that kind of a case, you might make that database a separate configuration item, not because it logically should be, but just so you can keep their hands off of the other stuff. Keep them out of it. In other words, very often, part of your job as a manager is to keep the boss and the customer from poking their nose in stuff that just messes everything up. You want them, okay, if you want to pay attention to the database, we'll have the database as a separate configuration item. So you don't have to look over here, you can just look at the database. Okay, here's another thing to consider. If two different contractors, two different companies are going to build different parts of the software, normally you would have separate configuration items for each. It would be very difficult to manage if two different companies were building parts of the same configuration item. So you might draw a line and say, okay, that's yours, that's mine. Different target processors, that they run on different processors, that might be a good reason to make them separate configuration items. Different languages, we talked about that already. What about schedule and delivery dates? If one part of the software is to be delivered a year before another part, or one part is delivered in the first release and another part is not delivered till the third release, chances are you want to make them separate configuration items. You don't have to, but this is just something to think about. What about maintenance? How am I going to support and maintain these things? Typically, you maintain each configuration item separately from the others. So that might influence your decision. How big is the configuration item? You don't want it to be too big. Now, how do you define too big? Well, it should be something that you can get your hands around, that you can manage, that you can have a project to be in charge of. If it's really gigantic, you know, all the software for an automobile is too big to be a configuration item. The software that is used for the anti-lock brakes might make sense as a configuration item because it has a very focused purpose. Also, interfaces to other products. You want each configuration item to have as simple as possible its interfaces to the other parts of the software. Okay, so step 3 of system engineering is to build the parts of the system. And conceptually, the system engineer says, okay, you electrical engineers, you build these configuration items, and software engineers, you build these configuration items, and mechanical engineers, you build these configuration items, and then that's what step 3 really consists of. And the system engineer's job is to keep an eye on all that's going on, make sure that if there are debates about interfaces or how these different parts work together, that they're on top of that and make sure they resolve any issues that come up. And then finally is step 4, which is integrate and test, which is you take all the different parts and put them together. That's step 4. Step 4 is what I call the proof that you did good system engineering. If you did good system engineering, then when you get to step 4, all the parts come together. If you did poor system engineering, when you get to step 4, you have all kinds of problems because the different parts don't work together. You didn't define the interfaces properly, whatever. And if you get into trouble in step 4, the problem is you made the mistakes in steps 1 and 2, and you have to go back and do a lot of correction. Okay, how to make sure software fits the system? Well, in an ideal world, there are 4 things you should have to start a big software project. Now, this is not always true in real life, but conceptually you should pay attention to these 4. You want all 4 if you can get them. You want them as complete as they can be. If you don't have them, you may have to create them. And make sure you have access to the information needed to define them. And if somebody else is responsible for these things, make sure you have a good communication path to those people. So, for example, one of the 4 is going to be your system requirements. Well, if you don't have good system requirements, you want to make sure you can communicate with the person responsible for giving you requirements. So you can, when they make changes, they'll let you know and stuff like that. The first thing is a software statement of work. It's the requirements for your project. It's not telling you what the product has to do. It's telling you what your project has to do. You have to develop this, you have to develop this, you have to deliver this, here's when it has to happen, that sort of thing. Think about the statement of work you have for each assignment in this class. Each assignment has a statement of work. And if you read the statement of work, you'll notice there's a section that says tasks you have to perform and a section that says deliverables. Those are the essential parts of any statement of work. This is what you're supposed to do. This is what you're supposed to deliver. It doesn't have anything to do with the requirements. It has to do with what you're supposed to do. That's the statement of work. Now, very often there is a system level statement of work, but not a software statement of work. In which case, the software manager has to read the system statement of work and derive a software statement of work. And that means you write a software statement of work. It doesn't have to be fancy. But then you run it by the system engineer and say, is this what I'm supposed to do? Have I left anything out? And it's very important to get that information down, because think about the statements of work for the assignments in this course. I made it very clear this is what I want. This is what you have to do. And that's what a statement of work is supposed to do. The second thing, of course, is software requirements. And these are derived from system requirements. Somebody allocated certain requirements to your software, and what you want is for them to say, these are the requirements that you have to do. Now, very often, you have somebody develop your software requirements specification as part of the software process. But in a theoretical sense, they're supposed to hand them to you. In practice, you may have to go get them. You may have to get system requirements and extract information from what you've been able to gather and produce software requirements, and then run it back to the system engineer and say, is this what I'm supposed to do? Yes?
The business plan is often similar to the master plan?
The business plan. A business plan is kind of like a system level document for a certain kinds of business operations. And it would be done typically by a person called a business analyst or a system analyst. And it's not usually a technical document. It's usually more of a, covers the non-technical parts of a project. How are we going to market it? How are we going to sell it? What kind of outlets? That sort of thing. But exactly what it means may depend on the kind of business you're in. I mentioned before that a lot of the terminology varies depending on what kind of thing you're doing. That's a real problem in the sense that if you're in one kind of business, the terminology may be very different from another. But a business plan is generally a non-technical document, as I'm familiar with it. It's typically one of those documents that a project manager worries about. And a software manager has to understand it, but typically they have to make sure their software is consistent with that plan. But it varies quite a bit. Okay, the third thing you need is the system design. And exactly how that's communicated to you depends quite a bit on the nature of the system, how big it is, whether it's an automobile versus like a military vehicle or a factory or whatever it is you're building. It can come to you in many different ways. And you talked about a business plan. Well, sometimes it's in that form, but usually there's a technical design document of some sort or some technical design information that says these are the components, here's how they relate to each other, here's how they interface with each other, that sort of thing. And you need to know that because you're writing software that's part of this, and it's important for you to understand how what you're doing relates to the other parts of the system. For example, your software is used to test this hardware, which is used to enable this function. And you might want to understand how that works because maybe you have a deadline you meet and you got to say, which functions do I need to really implement in order to be able to do a certain test or whatever it might turn out to be. And the final thing that you would like to have in this ideal world is an ability to trace between the original requirements and what you're actually doing. Now, requirements tracing is a complex process. There are tools that will do this for you. But in an ideal world, you want to be able to say, this requirement for the software is traceable to this product requirement. And I'll say more about that in a little bit. And one of the interesting problems I've had, I did a little experiment a couple of years ago. I told students these four things, and I said, draw a picture of how they relate to each other. And I got dozens of different design pictures of how they relate to each other that were different, but were all valid, because it all depends on your point of view. So here is one of those pictures. The process of producing software begins with inputs and produces outputs, some piece of software. And your job as a software manager is to make that happen. And how these things relate. Well, the statement of work tells you specifically what you're supposed to do inside this box. The requirements for the software tell you what the product is supposed to be able to do. The system specifications are the basis on which your software requirements were derived, and your requirements trace mechanism connects everything together. Now, as I said, this is not necessarily the only way to draw this picture, and any way you draw the picture tends to not necessarily reflect all the things that are going on. But the idea is, let's suppose that you decide that a particular thing you're supposed to do cannot be done. The computer isn't fast enough. The requirements trace enables you to go back and say, which system requirement can I therefore not meet? So that you can talk to the system engineer and say, we don't have enough bandwidth on the network to be able to do this, and therefore we can't meet that requirement. The best we can do is such and such. And then the system engineer can go back to the original customer and say, you wanted 40 transactions per second, the best we can do is 32, whatever it might turn out to be. But connecting between the way the customer sees it and the way the system engineer sees it and then how the software engineer sees it is why you need a trace mechanism. You want to make sure that you pay attention to all the different customers. I'll say more about that later. There's not just a system engineer. They're not just an end user. There's various other people involved, all of whom think they know what's supposed to happen. And you need to understand all of their perspectives. You also need to know who's in charge of changes. If somebody decides to make a change in the design at the system level, who is that who will make that change? Why? Because if it affects you, you need to know who you need to be in communication with. In a big system, somebody may make a change and not think it affects software, and then you didn't know that the change was made, and then you made some software that doesn't work right. Understand the dependencies between you and other parts of the system. And we'll say more about how that's done. The software statement of work should say what are the entry criteria for the software effort, what are the tasks to be performed, what are the deliverables to be produced, and what constraints exist. For example, you have to get it done within a month. You have to get it done for under so many dollars. You have to get it done on this type of computer. You have to get it done within a certain amount of memory, whatever the constraints might be. And sometimes those are defined in a technical document. Any standards you have to meet. If nobody gives you a software statement of work, you may have to produce one by taking a higher level statement of work or whatever information you can gather and creating one. And then you go back and you say, is this what you want me to do? That's a very common scenario, is that they aren't very precise, and so you have to do that. In fact, here's the way it works on a lot of government contracts. I've been on several like this. The government says, we want somebody to build let's say a radar system that can be used on helicopters for search and rescue operations. And we want it to be able to do such and such. You write the statement of work, and then we'll tell you if that's what we really want. And so you, knowing what you're capable of doing, write a statement of work for yourself, saying I've got to do this, this, and this, and I'm going to produce this, this, and this, and you go back to the government and you say, is this what you want? And the government will often have 3 or 4 different companies bidding on this contract, and each one of them will produce a statement of work. And then the government will look at all 4 statements of work and say, okay, this company over here clearly doesn't know what they're doing. Let's just cut them out of the competition. These 3 clearly do know what they're doing, so we'll produce a statement of work that is the best of all 3. So they might take parts of your statement of work and parts of somebody else's statement of work and put them all together and then say, that's what we want you to do. So then you have to figure out, how can I do all those things that the other company's better at than I am? But that's the way it works in that situation. But the point is, you may have to write your own statement of work. In theory, software requirements are produced by systems engineers. Again, we're talking about big projects where they're not produced by customers or by software people talking to customers. They're produced by somebody higher up in the hierarchy of the product. In practice, they are often not very well written. They're vague, they're incomplete. They may look good to a system engineer, but a software engineer looks at them and says, that's not very good requirements. I can't work with that. And so what do? Well, one thing you do is produce what's called a thin specification. This is where you take everything you know and put it in one place and then gradually flesh it out and add detail. Another thing you do is rapid prototyping. You work with the customer to produce a quick and dirty prototype of what you think they're asking for and then say, is this what you want? And another way is to just come up with a highly iterative life cycle where you go through a first iteration and show them something and then they change their mind, and then the next time around you do something a little different. Okay, there's lots and lots of different kinds of software, and they all may have different approaches that you might want to take as far as your development process, for example, or your life cycle. So if you're in charge of the software on a project, you need to make sure you identify all the kinds of software you're going to have to be responsible for. For example, if you're in some kind of a demonstration phase or a prototype phase, your software may be throwaway software designed to demonstrate that something works, but not designed to be robust and high quality and suitable for putting in a final product. The focus may be get it working quickly to demonstrate something. You typically don't worry a whole lot about extensive testing, reliability, and all that kind of thing. You just try to get something to work. An evolutionary prototype is where you build a prototype and then keep refining it till it's acceptable. And in this kind of situation, the software is not intended to be thrown away. It's intended to be refined until it's reached the point where it's usable. So in that case, you pay a little more attention to things like, is it testable and do we have good quality and all that. Production quality software, in most cases, is designed to be very robust, designed to be solid, dependable, reliable. Let's say you're building software that's going to go on a space shuttle. You don't want it to crap out, pardon my language. You want it to work. Because if the space shuttle collapses because your software has a bug in it, that's a lot of expense. So you put a lot of emphasis on high quality, high reliability in this type of software. Test software, software whose purpose is to test something else. You may want it to be functional and to be correct, but it doesn't necessarily have to have some of the characteristics of production quality software. Simulation software, software whose purpose is to simulate something else. Again, the idea here might be make it very easy to modify and to parameterize, but it doesn't necessarily have to be fast. One of the things about simulations is how easy it is to change it is intentional, because you're trying ideas out and then changing ideas. But there's some dangers we'll talk about. Here's one of the dangers. You have a simulated environment, and based on that you come up with specifications for the system. Then you develop the system, and then you test the system. And the way you test the system is you run it against the simulation. Well, the problem is it takes some time to get from here to here. And you've got a bunch of people who developed the simulation over here on the left. And what were they doing in, let's say, the 3 or 4 to 6 months or so between the time you did that and the time you did the thing on the right? Well, they probably diddling around with the simulation. And therefore, the one that you're running against on the right is not the same as the one that you started with on the left that defined your specifications. And so it may be that it's impossible to pass your tests because the simulation has changed. Simulations are designed to be easily changed. But unless you're careful, you can get yourself in a trap here. Tools are another kind of software. They're found everywhere. A lot of them are just temporary. You build a quick and dirty spreadsheet to accomplish something or whatever it is. And therefore, they're often very sloppy in terms of accuracy and correctness and so forth. Debugging software, you're probably all familiar with using such software. But again, depending on what you're debugging, it may or may not have to meet certain performance requirements. Installation software, designed to support installation of the product on the end environment. Generally isn't so much focused on performance as it is on doing a fairly straightforward function. There's all sorts of other stuff here I won't go into. The point is there's all kinds of software, and as a manager you have to say, which kinds of software do I have to support? And some of this stuff you may say, well, that software makes sense to use structured programming, and that went over there, we should use a Scrum method, and that method went over there, we should do something else. You don't want to just use the same method of developing software on all these different kinds because it may be inappropriate for some of them. Deciding what kind of software you have is an important function of the software manager. And you want to make sure you work with the system engineers in defining that. Okay, to summarize this module, system engineering life cycles incorporate multiple disciplines. They determine what the functions are and what the components are that implement those functions. And a key part of that is defining the software items or software configuration items. And that's where the software manager or the software technical leader really needs to be involved. I talked about 4 items that in theory you should have to set the stage for successful software development. You don't necessarily always have all 4 of them, but you want to think about, if I don't have all 4 of them, what am I missing? What information would I like to have that I don't have? And you also have to define the kinds of software that you're going to use. Okay, that's the end of this module. As I said earlier, the modules at the beginning here are quite high level and conceptual. We have one more of those, and then we're going to start, next week, we're going to start getting more focused and more detailed. Okay, it's time for a break, and knowing how the students in the classroom react to breaks, I am going to make this a 5-minute break. Okay, it's time for Module 5. And before I begin, let me just make an announcement. Several people have asked me about this. There's a due date for every assignment, and it's usually the same day as the class. However, since this class is on Monday nights, usually I do not have a chance to grade assignments until the following weekend. So if an assignment is due on a Monday and you turn it in on a Thursday or a Friday, usually that's just fine. Now, also, if you turn it in on Monday and change your mind and by Thursday you say, no, I did it wrong, I want to do it differently, you can resubmit most assignments. And if it won't allow you to, let me know, because Blackboard is really weird about this. It has all these trying to use Blackboard is like trying to fly a 747 airplane. It has so many different options that it's really easy to inadvertently get it wrong. But anyway, so you can resubmit things. But if I've graded something and then turned it back to you and you resubmit it, usually the first grade is the one that matters. It usually takes me a few days to reach. Okay. Now, let's talk about the penalty for something being late. The penalty for something being late is that you may not get graded right away. So, for example, assignment 1, I have planned to grade this coming weekend. Now, I'm going to grade a few of them this week if I have the time, and I may have the time. But my plan is to grade it this coming weekend. Now, if you turn in assignment 1 in a week, after I've graded all the assignment 1s, I may be off doing something else, in which case I have a couple of assignment 1s that are late, and I don't have time to grade them because I'm grading assignment 2 or something, or maybe preparing the lecture notes for the next lecture or whatever it might happen to be, and therefore I may not get to your assignment 1 for another 2 or 3 weeks. So the idea is if you turn it in on time, you should get it back in a timely fashion. If you turn it in late, you may get it back late. So that's your penalty for being late, is to get it back late, which often is a big deal. So just so you understand my rules about that. I don't give penalties for being late in terms of grades. I give penalties in terms of getting the thing graded. Where this tends to matter the most is at the end of the semester, especially for students who are trying to graduate or who need to get a grade in order to get some financial aid or something like that. You know, if you turn it in a month late and I don't get it graded for 3 months, you might be out of luck. So just thought I'd give you the rules on that kind of stuff. Okay, now let's talk about software development life cycles. We're going to talk about different kinds of life cycles, and you'll notice there's a lot of different pictures. I pulled, if you search for software development life cycle on the web, you'll get dozens and dozens of them. And part of what you have to do as a software manager is to decide what life cycles am I going to use on my project. So I'm going to talk about a few of them, but I have to tell you that there's so many out there that I can't claim to cover all the territory. The life cycle is the top level view of the software process. And the life cycle you choose should fit a particular set of situations that you're dealing with. It's something that the software manager is usually the ultimate decider on. Remember, we showed this diagram earlier where there's all sorts of different software life cycles for different kinds of software that you might have to develop. Well, there's also a concept known as tailoring, and what that means is that you take a sort of a boilerplate standard life cycle and then modify it to fit your particular situation. We'll see some examples. Let's suppose you have 4 software things you have to do: a simulator, some factory test software, a mission software or application, and then support software. And you're considering different life cycles. Well, you might want to look at them and say, well, this life cycle makes the most sense for these 2, and this one makes the most sense for this one, and this one for this one. And so you may, in this example, have to support 3 different life cycles. That's fine, you think that's the most appropriate thing to do. One of the things that you should think about is how often will the software be used and how critical is its functionality. So at one extreme, you have something that is incidental and throwaway. For example, put together a spreadsheet to do some simple calculation that you need along the way, and that's all you need for. It doesn't have to be very fancy. At the opposite extreme, you have something that's going to be used in deliverable products and reused over and over again many times, and it's life critical. If it fails, you could kill somebody. Maybe it's a module that you use in a medical application. Well, you want to make darn sure you did that one right. Okay? And then there's everything in between. And by analyzing it this way, you can kind of gauge where I need to be in this spectrum. Let's talk about entry criteria for your software lifecycle. You should have a goal. What are we trying to do? And can we measure it? Can we tell whether we have done it? Now, measurable doesn't have to be a number in this case. It's got to be throwaway. Well, you can certainly tell whether you can throw it away. But if it's going to be production, it means you can't throw it away. Then that might mean a different thing. Why are we doing it? What is it supposed to accomplish? And you need to think about that. What is the intended use of the software? What standards are going to be applied? As a simple example, do you have coding standards you have to follow? Another case, if you're writing the software for a European organization, you have to meet something called ISO 9000, which is a quality standard that is required on products you sell in Europe. And what are the deliverables? What do I have to produce? Again, the statement of work should tell you most of this. If the software has requirements that are known, then you are generally safe in using what's called a sequential development lifecycle. Meaning you start with the requirements, do a design, then you write the code, then you test it. If the requirements are not known, which is more often the case, or some of them are known and some of them are not, then you are probably going to want to use what's called an adaptive or iterative or incremental kind of life cycle, where you do little bits at a time. In an ideal world, requirements should meet a number of criteria, and here are some of them. Complete, meaning every requirement is known and it's clearly allocated to you. Sufficient, that means every required feature has been specified. Consistent, no two requirements contradict each other. Unambiguous, there's only one possible interpretation. And testable, you can tell when you have satisfied the requirement by running a test or doing something else. Now, this is, as I said, in an ideal world. In practice, you aren't going to satisfy all these. But if you know which of these you don't satisfy, it can help you decide what life cycle model to use. Some requirements will be unknown, and there's a terminology called TBD, to be determined. A TBD requirement is something you know is there, but you don't know what it is yet. For example, let's suppose that you have to support end users on a system. Let's say you're building a database or a web application, and you have to be able to handle a certain number of users. Well, they may not tell you yet, they may not know yet how many users you have to handle, but they may be able to tell you that there is going to be a requirement for how many users you have to handle, but you don't know what it is yet. Or that maybe you're writing software for anti-lock brakes in an automobile, and you need to know how fast it has to respond, and they haven't told you that yet. Requirements can be wrong. Requirements can be missing. Requirements can be unclear. Requirements can contradict each other. Requirements can be not testable. Requirements can change in midstream. Why would requirements change? Well, you might have new technology. The customer might have a different understanding of their problem, or you might change, the problem might change. Sometimes you don't know until you get into the problem what the real problem is. So you typically don't have the ideal world. Now, how do you handle these imperfect requirements? Well, define an adaptable life cycle that will accommodate requirements changes. We're going to talk about some life cycles in a moment. Assign someone to be responsible to manage changes. In other words, don't just arbitrarily say, okay, we'll do that, we won't do that. Have a person responsible for sort of maintaining the current requirements. And when they make a change, they have to let people know. When they're going to make a change, they have to make a decision, and they have to get the right people involved in the decision. One of the most successful software managers I ever worked with was a woman who had the following rule: no change can be made to the requirements without my signature on a piece of paper that says the consequences of that change. And she would send that to the system engineer or the customer and say, the change you just requested is going to add 3 weeks to the project and so many dollars. And they could go ahead and say yes, or they could say no. But the point is, she wouldn't let them change a requirement unless she had written that document telling them the consequences of that change. Now, that was a smart woman because she knew to let the customer understand the consequences. Now, how did she know that? How did she know that if you make this change, it's going to have these consequences? Because she had an excellent requirements tracing mechanism. When the customer said, I want to make this change in my requirements, she could trace that down through the system requirements down to her software and say, these 3 modules need to be changed in the following way. And she could go to the programmers and say, what's going to happen if we have to do this instead of that? And sometimes it would be, well, we already wrote the module this way. We're going to have to scrap it and redo it. Or sometimes it would be, no, we haven't started that yet. It'll be an easy fix. But the point is, she could very quickly come back and say, here's the consequences. And that's good management. She understood what the consequences of change would be. Select a life cycle based on the level of expected requirement stability. If you expect requirements to change a lot, be more iterative, more adaptive. If you have to be determined requirements, see if you can get ranges for them. For example, suppose somebody said, I want you to build a database that will store student records for all students at SMU. And you say, well, how many student records is that? And they say, we don't know yet. Well, you could say, well, please give me an upper and a lower bound. It won't be any worse than this number, and it'll be at least this number. Because if it was only the students in this class, heck, you could do it in memory. You wouldn't even need a database. If it was all the engineering students, you'd probably need a database. If it was all the students at SMU, it would be a bigger database. And if it was all the students who have ever attended SMU for the last 100 years, it would be a much larger database, right? And you'd have to do a lot more things in your design. So see if you can get the customer or the system engineer to give you the upper and lower bounds on a requirement if they can't give you the exact requirement. And of course, you want to work to eliminate the wrong and missing requirements. Interface requirements. These are sometimes even more important than the requirements for the components. How does your software interface with everything else? What protocol, what kind of communication, what speed, et cetera, et cetera, et cetera. Why is this important? Because the interfaces are going to determine whether the parts are going to eventually come together. There are many development processes that say the very first thing you have to define is your interfaces. For example, if you're going to develop certain applications for a web-based application, they'll tell you you have to follow these protocols and have to write it in these languages, and it has to work this way and this way and this way. And then you could go ahead and write your application, but it has to meet these standards. When Apple comes out with a new iPhone, they publish standards for interfacing to the iPhone. If you want to write an app for an iPhone, you have to do this, 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 and this, and this. They define the standards. They don't care what your app does, but they care how the app interfaces with the rest of the iPhone. And the reason for that is that way you can have a solid set of interfaces and start putting applications in there and testing them out, and if they don't work, you go fix the app to fit the interface. You get the interface issues resolved early. Very, very powerful technique. Okay. If possible, requirements should be contained in a single document. Why? Because too often the requirements appear in multiple documents, and then you make a change in one document, but you don't make the corresponding change in another document, and then things don't work out right. Who's responsible for requirements? Well, this is an interesting issue. I alluded to this earlier. There's a bunch of people known as stakeholders. They are people who care about what you're doing. And here are some of them. The end user, this is whoever it is who has to use the software you're writing. The champion, this is the person who's paying for it. This may be somebody in a company who's buying something from you or whatever. Marketing, people who have to sell the software to somebody. Accountants and lawyers whose focus is on protecting you from being sued, but in the course of doing that, they sometimes put ridiculous requirements on you. Then you have what I'll call the wild card factors. A manager who promises features to the customer without understanding the consequences, and then expects you to implement those features. This can happen. It happened to me many times. Engineers who know better than the customer and therefore put in features that the customer doesn't want and that add cost and add risk and don't really sell any more product. But the engineer thought they knew how it should be. All right, we talked about this diagram, and here's applying it to software. The software process is looking at more detail than the life cycle. And let's take a look at this situation right here. The coding phase consists of doing these things. And here's your high-level process. This is what's called a waterfall process. It's a very sequential process. Define the requirements, design it, code it, integrate it. Suppose you had an iterative or adaptive process where you went through this cycle here multiple times. Maybe you go through 10 iterations or more. You would still do this part perhaps exactly the same way each time. So you can document this detail level process and say every time we go into a coding phase we go through these steps, even though our life cycle may involve going through the coding phase 10 times. Now let's talk about the idea of tailoring. There's a process called understanding the need. We're going to talk about that next week, where you try to figure out, of all the possible life cycles that are out there, which ones make the most sense for me. And then you do what's called tailoring, which is making it fit your specific situation. And here's an analogy. You go into a clothing store and they have all racks and racks of clothing. And so you look through the racks of clothing and you say, this is something I would like to wear. It's the color I like, and it's about my size, and blah, blah, blah. So you pick that, and you try it on, and you say, yeah, I think I'm going to use this. Except that it needs to be altered. It needs to be tailored. This part needs to be made a little bigger, and this part needs to be made a little smaller, and the buttons need to be moved around. And that's the tailoring process, where you make it fit better. And that's the two steps you go through as a software manager to decide on your process. The first step is selecting a basic lifecycle model. And then the second step is doing the tailoring to make it fit the circumstances. For example, let's suppose you decide, I'm going to go through this particular life cycle, and I'm going to make it an iterative life cycle, and I'm going to go through it 6 times. And then for your tailoring, you say, I'm only going to produce the documentation on the 6th time, because the other times it's just temporary. So it's like 5 prototypes and 1 final. So that would be an example of how you tailor it. We'll see more examples of that. Okay, the V model is sort of the most general model of the software development process. And I like to think of it as not so much the way you develop software as kind of an explanation of what's going on in the background. Almost all other models can be thought of as having this as an underlying model. The idea is you figure out what you're supposed to do, design it in more detail, implement it, which means write the code, then you test it at the unit level, and then you combine the parts of the software together to test it at the all software level, and then you have a final acceptance test where you run the software on the final hardware and see if it all works. Now, again, this is a concept here. The idea is that when you do the acceptance test, which is the final test before the customer accepts the product, you are testing against the requirements as originally specified by the customer. Remember we talked about how requirements should be testable? Well, this is where that comes into play. This is where you have test cases based on the requirements that are derived from your original requirements, and those tests are run at the end to make sure that you satisfy all the requirements as the customer understands them. Then when you produce a design, you produce tests that all are based not only on the requirements but also on the architecture. Tests based on the way you designed it. And those are used here. And then when you get to the detailed design, you have tests based on the detailed design, which are tests you run here. Now, again, this is a conceptual model, but the important message on this slide is that test planning begins with requirements. There's an axiom from the Agile people think they invented it. They didn't really, but they think they did, and that is they call it test first. It means if you don't know how to test it, then you don't know what you're doing. People have known that for 50 years, and they have practiced it for 50 years. They just didn't call it that. But this is the same idea. If you don't know how you're going to test the requirement, then you don't have a good requirement. So that's kind of the V model. Now, all other models kind of fit within that picture. Here are some general categories of life cycle models. Linear models are where you do each step once in some kind of a sequence. And the most prominent one of those is called the waterfall model. We'll talk about that in a moment. An incremental or evolutionary model is one where you go through multiple times. You go through the same process more than once, each time doing something different, adding a capability, refining a design, whatever. An iterative is where you actually redo the product at each phase, whereas with incremental or evolutionary, you're actually adding capability each time around. Whereas with iterative, you kind of throw it away. It's like a series of prototypes. throw it away each time and redo it. And ad hoc is whatever seems to work. Now, think about learning to cook. Linear is you get the ingredients, you do the cooking, and you set it on the table and eat it, and you're done. Incremental or evolutionary is you do that once and decide maybe I didn't add enough salt, and then you try it again, and then the next time you make another improvement, and after 4 or 5 times you have what you want. Iterative is you build it, you make the first one, you think it's terrible, you throw it away, and you do it again, and then you keep doing it until you finally get one you like. Ad hoc is nobody can quite figure out what you're up to, but somehow or other you produce food at the end, okay? Now, one of the advantages of the first 3 is that you can learn how to do a better job. The last one, when you don't have a set approach and you do whatever seems appropriate, means everything you're doing is reacting to the circumstances, which means you may not be learning many lessons that you can apply the next time around. So that's not necessarily a very good method, but it's widely used, unfortunately. This is another way of describing this. You have at the left end the fixed and predictive, at the right end the adaptable and flexible ones, and in the middle you have the iterative and incremental ones. And on the left you have long phases, whereas you tend to have short phases on the right. Sequential on the left, repetitive on the right. Few requirements changes on the left, more requirements changes as you move to the right. Now, there is a very important model that just came out last year called the Software Extension to the Project Management Body of Knowledge. This is a document that explains software development to project managers. And those of you who are not familiar with it, the PMI, the Project Management Institute at PMI.com, is an organization whose focus is better project management, and a lot of project managers get certifications and training from Project Management Institute. And so this software extension is designed to teach project managers about software. And it was developed by some colleagues of mine at the IEEE Computer Society, and that's why I know so much about it. And this model, this picture that's on this slide, comes from that document. They have a slightly different version of the picture, but it's essentially the same. Now let's look at some specific life cycle models. And as we go through specific models, you might want to think, where do they fit on this diagram? And as a software manager, you want to think, given the nature of what I'm doing, where do I want to be on this diagram? Okay, there's the Big Bang model, which is an ad hoc adaptive model. You give the developer a statement of the problem, they implement something, they deliver results, and hope you're satisfied. No formality. This is a method that works okay for really small projects, and the bigger you get, the harder it is for this to actually be successful. The drawback is there's no consistency between different implementations of this model. Not much discipline, not much documentation. It's hard to transfer what you've learned to other people because it's sort of whatever comes to your mind. It's a model that may work for relatively small applications and very skilled developers. All right, the waterfall model, very interesting model in the sense that it's the first documented model where somebody attempted to actually describe what happens when you develop software. And I should explain that the guy who did this, Winston Royce, his son has written some papers on this. He has passed away. But he originally came up with this idea in the late 1960s. And he introduced it not as a life cycle model, but as a way to explain what's happening in software development. so you could explain to others what's going on. The problem is a lot of people took it as a life cycle model and used it, and some people found that it worked. But on the other hand, other people found that it didn't work. And then they blamed Royce for coming up with a bad model. But he didn't intend for it to be a model of how to develop software. He intended for it to be a way of explaining what's going on. And one of the most interesting things is that many, many models that have come out since then explain themselves by saying how they're different from this model. So it actually serves a very useful purpose, even if you never actually develop software this way. But let's talk about the waterfall model. The basic idea of the waterfall model is that you have a sequential series of steps. The exact steps don't matter. What matters is that they are sequential, that each phase ends with some kind of a milestone where you sign off and say, I'm done. And each phase produces some artifact that is passed to the next group of people who do the next phase. Now, imagine that you had a team of 400 software developers, and there were 50 doing requirements analysis, and 100 doing design, and 150 doing coding, and 100 doing testing, and so forth. This actually works pretty well in that kind of a scenario, because the documents that you produce at the end of each phase are the material you hand off to the next group so they can do their thing. Now, the first assumption of this model is that you have good requirements that aren't going to change a whole lot, because you do the requirements and then you're done. Then you do the design and then you're done. It also assumes good design at the system level, so that you're not constantly changing the system level design with consequences on the software. And here are typical phases of a waterfall process, the goals of each phase, and the exit criteria for each phase in a very high-level way. Just for reference purposes. I'm not going to go through the details here, but you might find it useful later. Each phase has goals and certain kinds of reviews that you perform at the end of the phase to make sure you have satisfied the criteria. The reference book by Futrell has a more comprehensive discussion of all this. A very important concept of the waterfall model is that different people could be assigned to each phase. You could have a design group and a testing group and a coding group. And this actually is a very good concept for a really big project. On the other hand, it doesn't work very well when requirements change a lot, or when requirements aren't very well defined. It also doesn't work really well for little projects where the same people do all the phases. It produces a lot of documentation, which may not be cost effective for a small project. And the way your software team works may or may not fit this type of approach. It would be interesting for you to look at each phase and say, what are the milestones, what are the entry criteria, what are the exit criteria, etc. In assignment 5, you're going to have to select a life cycle model and answer these questions about whatever one you choose. So you can think about that. Note this thing at the bottom. The exact phases don't matter. What matters is the fact that it's a sequential sequence of phases. The big plus of the waterfall model is that it's easy to explain. You can show it to somebody who knows nothing about software and they will understand what you're doing. It's also easy to synchronize with non-software activities. You can say, okay, we're going to have the design ready by this date. We can do this test by this date. Everything is kind of laid out. It tells you what to do without telling you how to do it. So you can use whatever method you want for design or coding or whatever. It includes all the basic tasks of software development. And it's very easy to adapt to new situations. There's lots of ways you can tailor it to fit new situations. Drawbacks. The first one is it assumes you have good solid requirements, which is not a very realistic assumption in a lot of projects. There's lots of reasons why requirements change. Often they're very good reasons, like you understand the problem better once you've started working on it. This guy named Andrew Taylor claims that 82% of projects that he found cited incomplete and unusable or unstable requirements as the #1 reason for project failure. So it's important to keep in mind that most projects don't have good solid requirements. These are the other things that Mr. Taylor found were the causes of project failure. Poor scope management, meaning you didn't understand the scope of the project when you designed it, and then it got way out of hand, much bigger than you thought it was going to be. Poor requirements definition, we already talked about that. Unclear objectives, you didn't really know what you were trying to get done. Remember last week I talked about the guy from Netscape who said the most important thing is to know what you're trying to do and what you're not trying to do. Unclear requirements. Lack of detail in requirements definition. You point all that out. A very common problem is somebody will stay a requirement that sounds perfectly sensible to them, but to you, you don't know what the heck they're talking about. It's not at all clear what they mean. Another drawback is that it assumes that you can do things sequentially. But in real life, you'll make mistakes and you have to go back and fix things. And it assumes the customer can understand the requirements specification and make sure that it's correct. This is what usually actually happens when you try to use a waterfall. It's called the waterfall with backflow, meaning you make mistakes in design and go back and fix them, and, or you discover mistakes during design that require you to go back and revise requirements. And then you discover mistakes in the design when you're doing coding, and you have to go back and redo the design and so forth. There's something called the waffle principle. And it has to do with the way you make waffles. And one of the rules for making waffles is you throw the first one away, okay? Because you have to get the waffle iron seasoned. And the first one, it tastes awful, but you throw it away and then start making it. Well, some people claim that this principle should be applied to software. You always throw the first one away because you'll screw it up. And there's a very good book called The Mythical Man Month, which if you haven't read, you should. There's a 1995 version is the one to get. And it explains all this kind of stuff. Very, very good book. All right, the spiral model is an incremental or iterative method developed by a guy named Barry Bain. We'll see more about him later in the course. Originated in the 1970s. The idea is to have a series of prototypes where you get successively more complete. And think of it as this. You start with the kernel that you're sure you know how to build. Then you take and build the risky components that you're not sure how to build, get them working, and then take another group of components that are not quite so risky and continue going around this spiral until you get it all done. It's very similar to the waterfall in terms of your objective, but the difference is going around this cycle multiple times. This is the way it was actually diagrammed by Bain, and it's a lot harder to explain it when you draw it this way. But Part of what he talks about is how to evaluate the risks and focus on the riskiest parts. One of the most important assumptions of this is that the requirements are clear but may change as a result of your prototypes. That, again, you have good design, but you may decide to change it as part of your prototyping activity. And that you know how to analyze and rank risks. We're going to see a lot more about risk later in the course. The big advantage is that it allows you to change requirements and helps you manage risk. And you can tailor this in lots and lots of ways. One of the most important benefits of any incremental method, starting with a spiral, is that you learn during each iteration, which means the second time you do a better job, the third time you do an even better job. By the time you're on the fourth or fifth iteration, you're really, really operating efficiently. Your team knows how to function as a team. You have avoided a lot of inefficiencies. You've made improvements. It's like anything else that you do. The more you practice, the better you are at it. Studies show that you can be 2 to 3 times as productive the second or third time or fourth time around, just because you got rid of all the inefficiencies in the way you do the work. Let's talk about drawbacks of the spiral. One of them is, in order to use a spiral, you have to tell your boss that you don't fully understand what you're doing. And many managers don't like that. They're very uncomfortable with the idea that these software people are going through spirals, and I don't know how many spirals they're going to go through, and they don't seem to know what they're doing. They're hoping to find out. That's the way it looks to the project manager. So you have a difficulty sometimes. It's hard to synchronize with the rest of the project. You got to make sure your spirals correlate to when hardware needs software to test it out and all this kind of stuff. So it gets to be a more complicated job. And it's hard to tell where you are and how much you have left to do, because you're not sure whether the current spiral is going to succeed, and if not, you have to try it again. And so it's very hard to say where you are when there's a project schedule and somebody says, how far along are you and how much more do you have to go? And you say, I don't know. It's hard to, so a lot of the time it's hard to convince your manager to let you do this. You also throw away a lot of code along the way. All right, there's something called the controlled iteration model, which is an attempt to deal with some of those drawbacks of the spiral. And I won't go into the details here. There's a reference that talks more about this. But the idea is it's like a spiral where you start the second one before you finish the first one, and you define in advance a little more about what you're going to do in each iteration. And this is the way it's drawn, and it's very hard to explain. This is one particular implementation of it called the rational unified process. The idea is that you go through these things multiple times, and rather than try to explain it here, I'll just refer it to you if you want to read more about it. The benefits are it's a disciplined iterative approach. It fits a lot of modern development tools very well, and it produces a lot of good documentation. But it's kind of cumbersome to use, especially for small projects. Rapid Application Development, or RAD, is another incremental technique where it's kind of like doing the spiral model, but in a different way. It evolved in the 1980s and 90s, primarily for people developing data communications and web-based applications. The big advantage is it produces new products quickly. It assumes that they have short lifetimes, like a website. And requirements change quite rapidly. The way you do RAD is you do a lot of reuse. You apply the same modules over and over again. This is a picture that sort of explains it. Instead of a waterfall, you kind of go around that thing multiple times, pulling things off of a component library and adding capabilities each time, and producing a usable product each time you go around the cycle. And I know that I'm not doing it justice, but in order to do it justice, I'd have to have a whole lecture on it. So this is just to familiarize you with the concept. It assumes that interface requirements are established, but the application requirements are fluid. Interface requirements like the protocol to use on the web, for example. The risk of quality problems is mitigated by the fact that your applications don't have long lifetimes. So if they're poor in quality, you throw them away and try another one. It's not like something you'd put on a space probe that's going to be flying through space for 20 years. It doesn't. This is not what you'd use for that. The big advantage is that it allows you to make changes in requirements very frequently and produces a reusable product each iteration. And that's really important if you're in the kind of a business where it's important to get something out on the street quickly. You also have the cycles of learning benefit that we talked about with the spiral method. Drawbacks: outsiders don't know what the heck you're doing. It can very easily be a very chaotic method. You don't do a lot of quality checking, and you don't produce a lot of documentation, which means that it's hard to produce stuff that's going to have a long lifetime or be maintainable for a long period of time. Agile development. There's a whole bunch of agile methods. Extreme programming, for example. You can think of them as lightweight versions of rapid application development. There's some really interesting stuff going on here in the sense that there's a lot of people who are very critical of these methods. A lot of these methods don't work very well. A lot of them work very well for very limited applications. For example, the project that originally came up with Agile, goes the C3 project at Chrysler Corporation, they threw it out about 5 years later because it wasn't maintainable. And so there's all kinds of pros and cons of these methods. This is the Dilbert version. I'll let you read it. This is, there's so much going on with agile development. There's so many people who are absolutely think it's the only right way to develop software, and there are other people who think it's a terrible method. And I don't want to be unfair about it. I just want to talk about a few things. It produces things in very short order. It says only do what you need to do. Don't plan the whole thing out because you're going to change your plans anyway. Here's some assumptions. Small co-located teams. Doesn't work very well with really big teams. Close customer contact. Doesn't work so well when you don't have close customer contact. Sometimes you're in an application where you can't easily communicate with the customer on a close, frequent basis. Customers will change their minds. A perfect product cannot be produced, so get something out and then improve it. That's the philosophy here. And there's certain situations where this makes sense. Here are some of the most important practices that are commonly used in extreme programming. Refactoring, which means you're constantly changing the design. One of the problems with that is that you're not constantly documenting your design, which means maintenance can be a real headache. Test first. I mentioned this before. If you don't know how to test it, you don't know what you're doing, you shouldn't start coding it. This is a really important concept that it turns out applies to every methodology I've ever seen. Pair programming. The idea is people work together in teams of two and they inspect each other's work. This is a very effective technique up to a point. Continuous integration. You define your interfaces and then add capability every day and keep the interfaces solid. So you're constantly integrating the system, and consequently you don't have big integration problems at the end like you frequently do in a waterfall type technique. Drawbacks. It's not always easy to be simple. It's easy to drop the discipline and become a very undisciplined hacking type of environment. Some things don't scale to large projects, like the need to have close customer contact. And it requires you to understand the design because you don't have design specs. And if you have a design that's really big and complex, that may not work so well. All right, to summarize this module, life cycle model is the top-level view of the process. There's many different life cycle models for software. I've just scratched the surface here. A process must be tailored to fit the needs of your specific project, and we'll say more about that. That's the end of the module, but I wanted to give you just tell you there's an appendix which has information about a bunch of other models. This is some of the agile models that are out there. And then there's a lot of references I have here, including some interesting websites that compare all different agile methods and stuff like that. That's the end of tonight's lecture.